Good afternoon, everyone. The program on the main stage continues. We are super happy to have this new talk on graph neural networks for fraud detection. We are super happy to have Fen and Tintin, who are senior data scientists at ADN. So let's go. PyData, let's catch the villains with graph neural networks. Please, some applause.
Hello, hello. Good afternoon, everyone. Welcome to our talk. Today we are going to talk about graph neural networks for real-world fraud detection in ADN. So let's get started. So first of all, please allow us to introduce ourselves. Fen, go ahead.
Hello, everyone. My name is Feng. I'm a data scientist from ADN, and I got my PhD in computer science. And my current interest is about GNN, of course, and deep learnings and how to apply these models to financial applications.
Yes. Thank you, Fen. My name is Tintin. I also work as a data scientist in ADN. I also got a PhD in computer science, and my research focused on deep learning, some NLP, and generative models. So what can you expect from our talk today? So there are a few takeaways. First of all, we will introduce our very challenging business problem. And secondly, we are going to explain our amazingly performing GNN-based solutions. And thirdly, we will walk you through how we put such a difficult model in production. And in the end, we will share all the juicy lessons learned, which we normally don't share. And in the end, we will have some time for Q&A. So, to start with, what is our business problem or challenge here? Let's imagine such a scenario. A few years ago, you came to Amsterdam for a very nice job offer. And Amsterdam is an amazing city. You start to settle here, and you feel like, okay, this is the amazing city, my dream city to settle, and I want to have a life here. Then you think about buying a house. Then you go to the Dutch house market, and you check all the house prices. Finally, you found a few dream houses, but they are so expensive. What can you do? As one option, one of our merchants, GoFundMe, which is a crowdfunding platform. So you can go to this website, create a fundraising event, and you can share this link to all of your family, friends, or even colleagues. And of course, it's a happy flow of using this platform. But things don't always happen as planned, right? So what if it's a fraudster who opens the account in this platform? What can happen? What if they have a big dream, but an illegal dream? They can use such a platform to do money laundering. They can cash out stolen credit cards, and they can request a lot of chargebacks and refunds. And that is not good. So how do we deal with this? In 2021, in ADN, we launched SCORE to fight against those frauds. So basically, it's a fraud detection tool which we use for two purposes. First, we use it as an external product which safeguards our merchants from seller fraud. And internally, we also use it to fight against financial losses. And here, this list is basically a high-level overview of all the fraudulent scenarios that we are currently dealing with. And we observed an increasing trend of seller fraud in those places. So let's recap a bit. How can we formulate such a business problem in a more technical context? So here we are dealing with a fraud detection problem. And specifically for the talk today, we are going to focus on the seller fraud on marketplaces and platforms. And our solution will be a supervised learning-based binary classification. And in today's case, it will be a GNN. And our input data will be all kinds of payment data that we have. And the expected output will be a binary prediction to indicate if a seller is fraudulent or not. Of course, we need to have a target. So our goal is to maximize our true positives, and at the same time, we want to keep false positives at a low level. So next, let me walk you through our GNN-based solution. So to start with, you might wonder, why GNNs? Because every time you hear about fraud detection, you hear about lots of business-driven business rules, or traditional machine learning models like random forest, like LightGBoost. But can we do better with the data we have? And the answer is absolutely yes. So just by looking at those two plots, on the left side, it is more like in the traditional setup, you see all the sellers are isolated, independent. But by leveraging graph, you can connect the dots by connecting sellers using their common shoppers. And imagine you detected seller 1 and seller 4 as frauds. In a traditional setup, that's it. The work is done. You can go home. But with GNNs, not yet. You can still investigate further. You can look deeper. If seller 1 and seller 4 are fraudulent, how about seller 2, 3, and 5? So by such a simple comparison, you can already see the power of leveraging graph. So next, I will hand over to my colleague Fen.
Thanks, Tintin. So to leverage the power of GNN, of course, we need the graph as input. Here, so what I want to do here is to walk you through an example. And let's start with a transaction table in PySpark data frame. So if you look at the table, it's very simple. It just has 2 transactions. The first one is on seller 1. Seller 1 receives transactions from shopper car 1 and shopper email 1. And the second one is a different transaction on seller 2, and it's from shopper car 2, but from the same email. So if you map to the graph view on the bottom of this slide, it's very simple. It's just 2 sellers share the common email, and they receive different payments from 2 different cars. So if we think about how to do this transformation from the table to the graph, to support that, we create an internal graph API to streamline this process. So we start with these transactions. And we have 2 functions called source by and destination by, in which you can define the vertex type. For example, in this case, the source type is seller, and the destination types are cars and emails. So we can convert this 1 transaction table to 2 tables, which are the vertex table and edge table underneath of the graph frame. You can also add in some measures or features on vertex table and edges. Like in this case, you can add a transaction count as a feature, and this feature will be added to the vertex table and edge tables. So now if we focus on the vertex table, so you can see they have all kinds of different type of nodes, like sellers, cars, and email. But if we look at back our problem, we want to solve seller level fraud detection. We want to create a graph which focuses on the sellers and how they are linking together. That's why we do another step, which is bipartite projection, in which we map the original heterogeneous graph to the seller projected graph. Another benefit of this way is we can largely reduce graph size to speed up the training. Let's look at the code, how we do this. So we defined another API called bipartite projection, in which you can define the features and how do you want to do the projections. Now, if you look at the right side of the vertex table is only about sellers and how they are linking together. Now, if you want to take a look on what's happening on the real data set, here I show you an example graph we use in production. So if you compare the top heterogeneous graph and the bottom seller projected graph, the vertex table size is reduced by more than 10 times. So it's a big save for us to support the training. And now if you zoom into the seller projected graph, we can see the degree distribution of the seller projected graph. It follows nicely as a power law distribution. And at the corner, those are the interesting nodes. We call it super nodes, nodes with a lot of neighbors or high degrees. We will talk about it later, how we deal with them. Next, I hand it over to Tintin for model part.
Yes. Thank you, Fen, for preparing such a nice graph data set for me. So now we need a model to fit into this data, right? So related to this GNN design. So how can you get a good model? Well, in our case, we started with a very basic GNN, which is GCN model. So if you look at the left side of the slides, if you look at the graph, the GCN structure, it looks almost the same as a traditional CNN. But the only difference you notice is that there is a graph convolutional layer. And on the right side, we show the difference between 2D convolution and graph convolution. So basically, in the graph convolutional layer, the node, it can leverage all the neighborhood information. But the size of the neighborhood is not fixed. So that's the major difference here. And what are the takeaways from us? So from our experience, we noticed that there are no best models, only happy model tuning. And our suggestion would be start with a very basic GNN to use it as a baseline model, which in our case, it was GCN, and it was already working pretty well. And you can also try with different graph convolutional layers. And in our case, we tried Graph Sage. So basically, the Sage convolutional layer from that paper. And it also worked very nice. And we also got lots of inspirations from the book Graph Presentation Learning from William. So highly recommended. But next, I do want to highlight a few very important decisions that we made, which helped us improve our model performance. So the first one is a bit recap of what Fen just described. So we created this seller projected graph, which significantly reduced our graph size. So that allowed us to speed up our training and iterate way more than before. And we defined our problem clearly as a node classification problem, meaning that we treated each of the sellers as one node in the graph. And we also want to highlight that we are dealing with a very imbalanced data set here. So we purposely gave higher weights to those positive samples. And in the end, we also want to highlight that we used this very nice deep learning framework, DGL, which also helped us a lot with the implementation. And in the end, I also want to touch upon our training approach. As you may have heard of, there are two very popular training approaches that are commonly used for training GNNs. One is transactive learning, and another one is inductive learning. I hope from those two plots, you can see clearly what's the difference. So basically, in the transactive learning, you see a fixed graph for both training and inference. But with inductive learning, those graphs can be separated. So because of that, inductive learning can be generalized to unseen nodes. And it is a very big advantage. And because of that nature, it is more suitable for larger graphs, because we can split the graph. So that's what we chose in the end, inductive learning. So because of that, our graph creation process looks like this. So every day, every experimentation date, we create 3 graphs in parallel. And as one concrete example, so here you see we have 3 graphs. For example, the training graph is based on the active nodes from April, and test from May, and inference from June. Next, I will hand over to Finn.
Thanks, Nitin. So now we have a data and a model. We want to put everything into production so that to create a business impact and put it to improve the performance of the score. First, I want to show you how the overall pipeline looks like in Adyen. So we always start with Adyen payment platform. This is a platform every day we deal with millions of transactions in real time and save the transaction data back to the Postgres database. And we have a process to inject the data to Hadoop HDFS file system. Then we move to the big data platform, in which we start with large-scale data transformation use Spark. And then the next step is to, based on different applications, we have different engines. For our case, it's DGL, to create a model and predict whether a seller is a fraud or not. And all these pipelines are built on top of Airflow job scheduling, and we run it based on different use cases. Can be monthly, weekly, daily, or even hourly. And then the result of this models, we further inject it to the customer area so that our merchants can see the reports, can see the model results, and review what's happening for their payments. And there's one more last but very important step, which is feedback loop. So that's how we collect the fraud labels from customer areas back to the payment platform and enable us to do supervised training and continuously improve our model performance. Let's now look at big data platform. That's the key part of our model pipeline. If we zoom into it, it has 3 parts. The first part, actually, Tintin just mentioned. We use inductive learning, so we can generate, train, test, inference graph in parallel. And the graph will be converted to the DGL format. And then we do model training and the prediction in the DGL. And the final step is we adding some business context matchers to the predictions from the GNN and generate the final seller fraud alert. One thing to mention here is that our GNN production pipeline is all building on top of open source solutions. And this can also be used for your use cases. And there are some interesting technical choices behind this thing. The first one is about the graph creation part. Basically, we have 2 options to choose from. One is Spark graph frames, and the second one is graph database. And we went for the Spark solution because it's ready to go for production. We have a lot of experience to use Spark plus Airflow to do our production pipeline in Adyen. Also, it's very suitable for our needs because we want to create a graph and features in a batch mode. We don't want to real-time update the graph. We just create it as a whole. And the second one is it's a tough call, actually, because we have 2 mainstream solutions for model training for GNN. One is DGL, one is PyG. The main reason we went for DGL is that it supports distributed training and graph partitioning. So we are not using it right now because we do nice bipartite partition to summarize the graph. But we do see in the future, near future, we're going to have some scalability problems. So that's the main reason we go for DGL. OK, so the last part of this talk, I want to highlight some lessons learned during our production journey. The first one, actually, we mentioned at the beginning, supernodes. So those are the nodes with a lot of neighbors. And it can be a lot of different reasons of being a super node. In our case, it can be a special seller. Like, it is possible there are some merchant official account is attached to every single transaction and use it to collect the commission fee. It can also be a data integration issue. For example, the merchant can just put a placeholder shopper email, like shopper@123.com. But we don't want to link on this node so that every sellers are linked together, which will result in a very big edge table, not scalable to train at all. And also, the main problem is it can significantly drop the performance of our GNN model. The main takeaway here is we recommend to have some graph cleaning with business logic. And also in the production pipeline, it is better to have a proper graph validation between graph creation and the model training to avoid any surprises in the production environment. And the next one is deeper shadow, which is a very classic question specifically for GNN. If you look at the figure there, the idea of the layer in GNN network is whenever you add one layers, you add one hop away neighborhood graph into the consideration. So you're adding more and more layers. Eventually, your GNN will capture the whole graph, which makes the problem like every single node will have the same embedding. So the model cannot tell the difference from each other. So what we recommended is to always start with a shallow network. It is much, much faster to train. And also, usually, it is already a very good baseline. And then you can gradually adding more layers on top of it or try other different technologies to avoid over-smoothing problem. Another thing I want to share here is reproducibility, which is nothing fancy, but we do need to set every single random seed as a fixed value so that given the same input graph, you always produce the same result. This matters a lot in the production environment. On the final note, if you ask us whether GNN worth it, of course, we spent a lot of efforts, and it was a big investment for us to put GNN in production. Like we have a standardized and scalable API to handle tabular data converted to the graph, and it was also a steep learning curve to build up the knowledge around GNNs, not only for data people, but also for product to sell this to merchants and have the same understanding of GNN. But still, it was a strong yes for us because it has a big business impact. GNN outperformed all the existing business rules plus models by a big margin. And also, it safeguards both merchants and agents from seller frauds. If you're curious more about this topic, we just released our technical blog on Agent Knowledge Hub, so you can find all the details there. Cool. Thanks again for joining the talk today, and now
we can take some questions.
Yeah.